There's just a lot of things you can do. Two applications that are super low hanging fruit are sort of like massive data crunching of running lots and lots of EVM computational data, backtesting, but then like some of the other things is actually fuzzing. You can literally just run way more tree searches than was possible on a CPU.
Scraping Bits is brought to you by the following sponsors. MEV Protocol. Maximize your ETH staking value with MEV ETH, exclusively on mev.io. And Composable. Execute any intent on any chain, coming soon to mantis.app. That's mantis.app. And Fastlane Labs, the only MEV and intent-centric team that has a daily deodorant application rate of over 68%.
GM everyone, my name's Tagachi, the host of Scraping Bits, and today I'm with Eito from GatlingX. GM, how's it going?
Hey, great to be here. Thanks for letting me on.
Thanks for coming on.
Yeah, no, it's exciting to come on after seeing you in person.
Yes, of course. It was long awaited, finally here in London. Just for the people that don't know who you are you and what do you do?
Yeah, so I'm Eito. I did a lot of AI and reinforcement learning stuff in Oxford before I started GatlingX. It was a sort of derivative of stuff I was working in already. And then I guess about GatlingX, what do we do? Well, we recently, unveiled what we've been building for over the last year or so, which is GPU-EVM, which is this, I guess, put very simply, it's the highest throughput EVM in the world by around 100x, which that has a lot of sort of foundational unlocks in, training AI models or L2 acceleration, MEV backtesting, all of these kinds of things. But it really started from sort of an AI angle.
Interesting. So what was the background before getting into GatlingX? I know you were at Oxford and you're doing RL. What was that kind of history like before getting into what you're doing now, and how you got into what you're doing now?
Yeah, so I did a lot of like robotics and game playing reinforcement learning agents and stuff like that. I think generally like that these kinds of things are really interesting to me ever since I saw the AlphaGo stuff in 2016 or something like that. And yeah, I've also worked in like full end-to-end reinforcement learning, self-driving car startups, and like did a lot of RL research. But I think for me, what was really clear to me even before ChatGPT was the fact that, I think this was around 2021, 2022, but it was clear to me that, AI felt like consensus even before ChatGPT. It felt too obvious. It felt like it didn't have a bear case. And so it felt like a bad industry to be in, mostly because, if something is consensus, then there's not that much alpha left in that particular thing. And I think there's always sort of these correct technological waves to get into of sort of like, if you were in AI in 2013, when GPUs were used for AI training for the first time, that was probably a really good time to get in. It's probably not the case now. And so that's why I moved on to like crypto. And then, very naively, I suppose, like I started with thinking, okay, how can you apply, I'm good at RL. How can you apply RL to sort of solve problems within crypto? That was like sort of the very smooth-brained thinking that I had. And then, I looked into it. I was like, okay, what are the big problems? And, I saw that security was like a very big problem. And so I was like, okay, let's try and solve that. And then I met David, who's the security researcher at EF. And, I talked to him about sort of this idea of like carrying out reinforcement learning. And then, I worked on it for a bit of time for my master's thesis. And then, halfway through, when I got started, I was like, okay, to do RL, it requires a GPU parallelized simulation environment. And that is like a fairly consensus thing in the RL community. Like, just to give some context, NVIDIA has this GPU parallelized simulation environment called Isaac Gym, which is mostly used for sort of simulating robots or sort of like physics and stuff like that. And
Yeah.
Isaac Gym accelerates the training process of reinforcement learning agents by around 100x to 250,000x speedups in RL training. And so this is sort of the
why
degree.
is that? How does it do that?
Yeah, so that's a good question. It's because of how, like, what the concrete bottlenecks are when you are actually programming with GPUs and training models. One of the biggest bottlenecks that you actually end up with is in the GPU to CPU communication bandwidth. So, in particular, through the PCIe slot is like how the GPU and the CPU translates, and often, because that's the slowest sort of memory channel, the more GPU, CPU like information transmission you do, the slower your training process gets. In other words, the speed up comes from two things. Number one is like, okay, just on a sort of core basis, in a CPU, you have 16 cores. In a GPU, you have around 10,000 cores, although it depends on which card you're using. So already from that, you get a pretty remarkable sort of increase in computational performance. And then, the reason why you need a sort of GPU parallelized simulation environment is like, okay, let's assume that you're running the simulation on the CPU. Well, every single time you're sort of doing a training step, you'll need to sort of ping the data from across the CPU and the GPU, where in the GPU you're actually running the training or inference or whatever ML workload you're running. And so this is kind of the intuition behind why you want a parallelized GPU simulation environment.
Because the transmitting the data from the CPU to the GPU is the bottleneck. Is that right?
Yeah, that's kind of right. And like the situation you don't want to end up in when you're working with GPUs is that you're using more of the CPU process than the GPU process, i.e. like, since the GPU is able to do way more work than the CPU, it's sort of like if the GPU does very little work and the CPU does more work, then, you're not...
Make sense.
It doesn't make sense, exactly.
When you have 10,000 cores just sitting there waiting to be used and you're using just the CPU cores.
Right, exactly. And, like a lot of the sort of RL stuff requires just a very intense computational performance. And basically because, I guess I should get into NVLink, but I suppose on a very basic level, like, if you just keep everything within the GPU and never go back to the CPU, that's way more effective just computationally because transferring data is expensive. I guess it's a very similar model to how, like, you want to imagine like a server client model, and then you often don't want to sort of keep pinging data back and forth between the server and the client. You'd rather sort of do everything in the server or do everything in the client. In this case, the server is the GPU.
Yeah. Instead of bringing them all to get like closer and closer, like co-locating nodes, for example, for the people in MEV and whatnot, where you go like from Japan to America or something. Instead of bringing them together where it's all in America, you put them all on like the same machine in whatever country you're in, basically. And that's kind of what's happening with the GPU CPU thing. Interesting. So then you're actually forced to program on the GPUs, and so if it's based on the EVM, right, you're going to have to put the EVM on the GPU itself by programming on the GPU. And I guess you use CUDA for that, the CUDA kernel.
Yeah, so CUDA is like the programming language. It's very sort of C++-esque. I mean, it is basically C. It's like a SDK that you need to like write programs that run on the GPU. And in particular, it helps you like orchestrate the relationship between the CPU and the GPU.
Interesting. So then you basically put the EVM on the GPU, and then you run, these tens of thousands of simulations on it, instead of being limited by, you're still limited by cores, I guess, but you have even more to play around with.
I mean, you have quite a lot more,
Okay, that makes sense why it's that much, more efficient then. Okay, so then what is the plan for when you have this actually on the GPU, what does that enable?
Yeah, so I think obviously we started with the AI stuff, and I can talk more about that in a second, but when you sort of fundamentally unlock the speed simulation capabilities of EVM execution, there's just a lot of things you can do that wasn't possible before. Like, in particular, one thing that is super low hanging, two applications that are super low hanging fruit are sort of massive data crunching of just running lots and lots of EVM computational data, backtesting. But then some of the other things, which I think will be more interesting to your particular audience and in particular sort of your experience, is actually fuzzing. Because you can literally just run way more tree searches than was possible on a CPU.
Yeah, you're just, again, 100x faster minimum. But then I think the thing with fuzzing, you still kind of got the bottleneck of the software. You still got to build the mutator and all that. So you're actually creating good fuzzing, I guess, sequences. I mean, you could just do brute force completely, but I mean, the aim is to narrow the search space, right? So how do you navigate your way around? I always refer this as the 4 pillars. How you navigate your way around these 4 pillars, which are, first of all, every single contract in EVM. Every single contract has, let's say, 10 functions. These 10 functions have maybe 4 parameters each, and they can all interact with each other. So how do you narrow down this giant search space, which is also stateful as well? And so it's a tough problem, because maybe something isn't vulnerable in one state, but is in another. And then you have to get it to that state to become vulnerable. So there's a lot to search for. Even with 10x speed, you still need the software to actually get to the point where the speed becomes useful. And maybe reinforcement learning comes into that, but I would love to hear the thoughts.
Sorry, just to make sure I understand your question correctly, your point is about the complex dependencies between the different Solidity functions? Is that actually what you're asking?
So to discover the vulnerabilities, how do you do that at the end of the day?
Yeah, okay. I mean, so on a very basic level, let's just start with the fuzzer, right? What does a fuzzer do? It's basically a very simplistic brute force. I would call it sort of, the way I like to describe it is it's a near uniform policy function for choosing particular actions. And what do I mean by a policy function? It's sort of given a state of a contract, how do you get to a vulnerability? And, you usually define vulnerabilities with invariants, which is sort of the classic way you do it in Solidity. And then I guess a good way to think about it is you just want to throw as many darts as possible to go hit the target, right? To essentially exploit the vulnerability and break the invariant. And the way in which execution helps is just by running all of these executions in parallel. So, I mean, the way you can think about it is you just run all these executions as its own concurrent run with its own concurrent state. And then you basically say, well, okay, these concurrent runs can go and try and find the invariant violation. And, just by the virtue of shooting the target with many more bullets, you're more likely to hit it. That's sort of the very simplistic view of how do we get better at finding vulnerabilities. But then the interesting part comes in with AI, where sort of what you can do is you can basically train a policy function, which has sort of ingested a lot of state data, and then basically has a probabilistic intuition about how to reach violations over multi-step transaction steps. So what do I mean by that? It's sort of a good analogy I always like to use is sort of, given a state of a chessboard, right? Traditional reinforcement learning agents for chessbots will try and find a sequence of moves such that it can lead to a checkmate. This is exactly the same thing here, where, given a state of a contract, we want to find a sequence of moves that are stateful such that you can find this path which leads to invariant violations. And the optimal thing to do is if you can train a policy function which is basically just like how likely are you to choose a given move in the next move. You want the policy function to be calibrated to whatever is the sort of optimal move that will get you closer to where a bug is, right? So I guess to think about it in chess analogy, it's like, does moving this knight to, I don't know, e4 increase my odds of checkmating the enemy? That's always the question you got to ask.
Right.
And you always got to ask it sort of over a very long time horizon.
Right. The immediate thing I think of regarding that is you would probably reach like a local minima or maxima, because maybe the unlikely thing is where the niche exploit is. So is there any way to retrace here? Or I guess since there's so many going for it, but the probability of going this may be higher objectively, but maybe the one that is lower probability would actually find the exploit. So is there any way around this then?
The best way to think about it is like the reason why fuzzers struggle, right? Like traditional fuzzers struggle is because they have no good policy function, i.e. your probability distribution defined by your policy function is more or less uniform. Now, of course, that's not quite true because they do stuff like coverage guided fuzzing, which, obviously tries and maximizes the probability that you reach new untapped areas of the code. But the sort of point of doing RL is that you skew the probability distributions down to the line as like down to the moves that maximizes your probability of winning, i.e. hacking the contract, right? Like a good way to think about it is like, yeah, of course, if you keep playing at any given point, if you just play any random move in chess, you're probably going to lose. And that's sort of what fuzzing is, I would say. Like where, it's not quite uniform, but you're sort of just going very randomly.
Yeah.
And RL is sort of the actual guidance based on statistical distributions of what is most likely to find the bug for you.
That makes sense. So if you have a function that's a read only and then, a write, then it would more likely go towards the right. And then giving a situation, would you do read or write again? It's just continuing down that line. So you wouldn't start the function with a read, maybe. It'd be like a low chance unless it affects some other functions that are writes. It would be kind of like that, instead of going for the view function that's made for a front end.
Yeah, I think it's a very different architecture to front ends and stuff like that.
I mean, just the read function. Like you wouldn't go for the read function that is
course.
used for the front end. And that's the probability distribution. Okay, that makes sense. Interesting. So then how do you actually... Is this just like a traditional RL model, or are you like custom RL? And why not go beyond RL and actually try and do something that's like completely different, like completely new, different model, different field? Or is that just not needed at this point?
What do you mean by a different model?
So like instead of, let's say, supervised learning, unsupervised learning, reinforcement learning, why not go into like evolutionary models or something beyond that?
I would put evolutionary algorithms within the same category as reinforcement learning. I'd basically say like evolutionary methods are just another way of doing the reward maximization and simultaneously trying to train the optimal policy function that maximizes the reward function. I.e., sort of, it's like it's different ways of creating a policy that can find bugs effectively.
Got you. And how do you determine what are the difficulties you come across when actually doing this, like with the models and also putting them on the GPUs as well? Are you putting the models on the GPU, or is that separate?
So this is where sort of the magic of NVIDIA comes in with stuff like NVLink, which is basically like this technology where, so I've talked earlier about how one of the bottlenecks in AI, or just GPUs in general, is that you want to keep the GPU-CPU communication minimal. But then the interesting thing is actually like NVIDIA's NVLink, which facilitates extremely fast GPU to GPU communication. And just to give some context, NVIDIA acquired this Israeli networking company that provided extremely fast optic fibers for like high frequency trading, and acquired them for like 7 billion so that they can hook up their like NVIDIA GPUs together so that they can communicate as fast as possible. And this is actually how like a lot of modern AI is achieved with stuff like, Llama and ChatGPT and all of the like, where, none of these sort of large language models are big enough to fit in any single GPU. And so what they do is they essentially connect lots and lots of GPUs together using NVLink and orchestrate them in such a way where, from a sort of developer side, it seems like you're operating with a single GPU. So you're like, you essentially have such low latency across the different GPUs to where you can kind of treat all the GPUs connected together via NVLink as just one single GPU. And the bot main is just going from the GPUs to the CPU.
Interesting. So it's like clustering them all together, and since the latency is so low, it acts as like one, basically.
Exactly. And, this is how like GPT-4 inference is done by running, quote, distributed computing across all the different GPUs and sharding them across and, carrying out operations, then pulling data and, all of this kind of thing.
Interesting.
The main reason why this is relevant to us is just like, now, at least in pursuing sort of the security stuff, you can basically take all of the, like, you can have model training in one GPU, and then you can have environmental feedback coming in the other GPU, right? Which is the GPU-EVM. And then you can have this sort of coordination where like, you can abstract all of this sort of implementation details of all of the stuff that's happening in the GPU in some like very nice Pythonic UIs and stuff like that. And then you can train AI models on it, which can really just learn and benefit from all of this sort of environmental feedback that you get.
Curious of how do you build any kind of corpus, or is that just not a thing with RL based fuzzing?
What do you mean by a corpus? You mean just like a corpus or like essentially like a coverage tracking mechanism?
Yeah, so like what paths you've done, then like a pretty common thing is like you slash the corpus in half, and then it covers again. So are you keeping any like recollection of, the paths you've taken, or are you just throwing them into the model and just letting it do its thing?
So like right now, we are not doing that particular approach, but this is easily something you can do because you can just sort of append it to the set of states being tracked by the RL agent.
I don't imagine it being on the GPU though. Or maybe it would.
It can be on the GPU. In fact, you want to do as many things as you can on the GPU. One of the sort of key things that just sort of going away from RL for a second, the fuzzer that we have built in, which, we're going to be releasing pretty soon, is like we had to write the mutators in the GPU, right? Such that you don't run into the PCIe bottleneck. And so, all the data stays totally within the GPU, including the mutation, including coverage tracking, and all of these things.
So what other overhead is there then when you're putting everything on the GPU?
Yeah, so usually it tends to be, GPU programming is always interesting because you sort of run into two different paradigms where like, sometimes you're compute bound, sometimes you're memory bound. Usually it's easier to get rid of being compute bound. And then right now with our like highly optimized systems, we are now fully memory bound. And that's actually the bottleneck that's preventing us from getting faster. But to be totally fair, like we've been we've been running all our tests on a L4 GPU. So we can actually probably go much, much faster. The results of the 100x GPU-EVM execution is just on a single L4 GPU. And so you can kind of imagine how nutty it would get when
we keep scaling.
Yeah, exactly. Across multiple GPUs with multi-GPU coordination. And there's just a lot of cool stuff you can do there.
Very interesting. And are you only going to be targeting... What actually are you targeting? Post-deployment, pre-deployment, pending, transactions, or all of the above?
Well, I think the beauty of sort of fuzzing is just that you can really go for it in every single area. Like, I think obviously on-chain fuzzing is interesting, but I also think it's just interesting tooling to add to, the entire pipeline of smart contract development.
That makes sense. Because a lot of things actually happen post deployment because there's so many test cases that you can't actually account for. When I deploy my protocol and, maybe 2 weeks down the line, another big protocol pops up, that's now a new case that I haven't tested for because it never existed. And people aren't accounting for every single existing protocol and the ones continuously being added to the blockchain. So I guess you could do both services, really, or all of them. The bottleneck with pending transactions is people do flashbots, so you can't actually see them unless you are a block builder that's partner with all of them. That might be a thing, but that's the only way because they are private and you can't see them without being a block builder. Pre-deployment makes sense. It's just you can't account for the future ones later on, but it does account. It is good quality assurance, probably better than. Actually, not probably. It will be better than any other auditor or any auditing team, just from the sheer amount of coverage you can get. Very interesting.
Yeah, for sure. We are still benchmarking some of the fuzzer results, but the early signs look really, really promising for being sort of the best fuzzer in the world by quite a margin, I think.
Interesting. Yeah, I think anyone that has the skills of crossing disciplines truly rule the world because it takes so long to gather such a hard skill like AI or crypto. It takes years. I think once you can learn quickly and figure out how to learn as well, then you can ramp up. But initially getting into something like AI where you need to learn math and you have to on-ramp on math and all these different topics and go into AI, it's a lot. So if you're able to do multiple disciplines, then you really narrow down that competitive field. And so if you keep adding more and more and you get alpha, the competition just eliminates itself, really.
I think AI is definitely one of those things where, I think it seems very simple because of sort of the LLM,
LLM craze.
LLM craze, but there's a lot of non-trivial, engineering, whether it be sort of multi-GPU coordination or sort of policy function optimization. I mean, I don't know how many people know this, but ChatGPT was also sort of improved with reinforcement learning called RLHF. And, they tried to move away from it with GPO, but now they're realizing that there are some tangible benefits to RL. And it's sort of this huge intersection of lots of different disciplines coming in together to make the magic work.
100%. And that's the best kind of engineering. It's crossing them all together.
I guess there's also something interesting to be said about, I think AI is sort of one of those workloads that have benefited from the implicit transition that went from sort of Moore's law, where you just purely ride the compute wave of sort of, CPU performance doubling every 18 months, I think was the original Moore's law statement. Which, has been slowing down for the last decade. The thing that has been progressing is actually the rise of GPU computing as a paradigm, and in particular, just how much flops are available for actually running those. And that's been more or less, it's called the Huang law, which is named after Jensen Huang, who's the CEO of NVIDIA. But, they show this graph. It's not totally fair, but it does get the point across about how, parallelism and sort of full integration of software along with hardware and coordination of lots of multi-parallel compute cores is what's giving you sort of this very exponential rise in compute capacity. And AI is in some ways riding that wave.
Definitely, 100%. How did you get into this GPU stuff? Because it is, I think, in my opinion, incredibly niche if you're not in the AI field, right? So you have to learn about the GPUs, which are electronics and, hardware. And then you have to also learn the programming language of it as well. And I guess it's a very niche case. So how did you get into this?
Yeah, for a lot of the really, really hardcore engineering, I'll give the credit to my co-founder, Hugo, since, he's way better than me at a lot of the GPU engineering. But I suppose the knowledge about GPUs just come from doing ML very, very seriously. The deeper you get into ML, the more it's just about ML ops, DevOps, and sort of GPU orchestration and data, of course. I would actually, one of the sort of slightly controversial opinions I have is there's only really been one tangible, real innovation since 2017. And there's been no new AI sort of breakthroughs since 2017, other than diffusion models. And the reason why I say that is mostly because, the story of ChatGPT and these large language models have more or less just been make model bigger. Like that
Yes.
is, fundamentally what the game has been all about. And to be fair, like OpenAI has been laughed at by the AI research community because they sort of said, oh, OpenAI is not contributing any sort of intellectually new contributions, but like sometimes just making the model bigger and doing all of this sort of nasty MLOps and optimizations around Onyx and CPU GPU like optimizations, writing custom GPU kernels is really the thing that moves the needle, especially in modern ML.
Definitely. So you think for the next, I guess, revolution of AI, it would have to be a new architecture for these models?
I'm no longer like at the cutting edge of these sort of architectural, like, what is the future of architecture? I think the answer will be some combination of like, multimodal models. I think Llama 3 showed something interesting, which is something like, that these 70B models were vastly sort of underfitted. And actually, if you just give it more high quality data, then it actually generalizes well, and these LLMs can learn. And then there's sort of the fringe work like Mamba and RWKV, which are sort of trying to propose a new architecture to like AI. And to be fair, I've seen results for Jamba, and it looks really, really promising. So it's kind of hard to say like where we are heading with AI architectures. One thing I can say is just like one thing that seems grossly sort of underestimated is just the value of search. And I think that will sort of be the next frontier of AI, as seen by also just like the entire Q star debacle when Sam Altman was fired as well from OpenAI.
Yes. And can you go more into search? I know you talked about in some of your articles, the two main things is search and learning, right? And then scaling that with compute. What is the search part?
Yeah, so I think just to give some context, like I think the thing you're referring to is sort of the bitter lesson, which is this like really famous blog piece that was written by a very famous like AI scientist called Richard Sutton. He sort of wrote the most famous textbook on reinforcement learning. But it like the bitter lesson is essentially this observation based on history that the most successful AI methods tended to be sort of general learning algorithms with no human priors, with no human sort of engineering done. You just scale up a general algorithm that works for general cases. And like the two methods that can sort of leverage that is search and learning. Learning is like the actual sort of you run backpropagation, you like train a model on some data. Search is more the process of like, okay, let's just run lots and lots of simulations of let's run lots and lots of simulations so that we can know what is the optimal thing to do.
Right.
Broadly, like, ChatGPT is learning where, you just fed it in all of the internet's text and learned like how to speak English and, be very smart from that. And search is more of the AlphaGo-esque technique of, you sort of like have a policy function and you run a Monte Carlo tree search across a large state space to search and then go find particular vulnerabilities.
The search is interesting because if you are doing a shit ton of experiences of, let's say, like we have a road and there's, I don't know, there's 10 different ones or 100 different ones, and just scale that up. If you already go down one and then let's say you find gold of a certain amount and you keep going down that one, you know for certain there's always going to be gold down there. Why would they go explore another one? It comes back to like the explore exploit dilemma, but I've always been curious about this. If you're guaranteed to know something's always going to happen, which is kind of what we do in our day-to-day lives, of wake up, you should brush your teeth, otherwise shit's going to get bad. Then why would you explore something else? And I guess that That's also what I'm curious in AI as well. It's, can you get to the point where you know this and just find something that's really optimal and for certain based on, like, I guess, facts? Because you're learning about other things without actually doing it, which I guess is actually just simulation of simulating what's going to happen without doing it. Sure. Yeah, I don't know. It's interesting.
Yeah, I mean, there's an entire sort of, like field, like subfield within reinforcement learning about, what is the correct balance between exploitation and exploration. The answer in reinforcement learning is something like, when you train a RL model, you initially start with a like maximum exploration and minimal exploitation. And then as the model learns more and it sort of learns and like it starts to win more consistently, then it then it varies this hyperparameter that sort of controls the balance between, let's say, like 30% of the time it will explore and 70% of the time it will exploit the best strategy. And like with regards to sort of like how does it generalize across to wider domains, this is where like simulation is actually really useful because, in the case of sort of software, like let's say EVM computation, for example, you don't need to guess or like you don't have any uncertainty about how the execution will go. You can just run the execution and see what it gives you, right? And so GPU-EVM is sort of this very interesting like state search explorer, or maybe said another way, it's sort of this like Monte Carlo tree search explorer that can like explore through multiple different states very, very efficiently. Even you can really incorporate sort of like this exploration versus exploitation just in its learning process, especially when you get the RL part working.
Interesting. What do you think is going to be then like the next, how can you like expand on RL then in terms of like the cybersecurity? But I think that's the first question. I'll ask another one that's relating to that. How can you make it better than just a typical RL model, I guess?
What do you mean by a typical RL model?
I guess just like the standard one you would use. Is there any like kind of modifications that would help specifically in, I guess, this EVM environment? Because, I guess the EVM environment is the game like AlphaGo, because you have rules and constraints, right? So there's only certain things you can do. And then I guess the follow-up question to that would be, what about applying that to the world? Because then you go from this game, well, I guess the world does have constraints as well. So just a lot more. But yeah, for the first one, is there anything that can help with game-specific RL?
There's actually an entire hierarchy around like different kinds of problems and where RL is effective. And games are actually like games. I'm including sort of cybersecurity in here because I actually it is very much like a game because it's purely in the software space, and the sort of the one of the metrics that matter is basically just what is the cost of simulation, right? The reason why that matters is something like, you want to be able to get environmental feedback, and the cheaper the environmental feedback, the more data you can get to train your RL model, right? That's ultimately the most important thing. And so sort of to answer your question about like, how can this expand? Well, the hard part is it's really hard to expand, actually. The RL is very specifically good at, sort of games or fully simulatable environments, or just more generally in environments where the cost of environmental simulation and data acquisition is extremely low, but it's not too useful, not too sort of effective in areas where, simulation is really expensive, just like the real world, right? It's very sort of cumbersome for like humans, for example, to give feedback. Actually, that's why, like, when ChatGPT was trained, the RLHF process came from like a bunch of data labelers in sort of low-income countries.
Right. That's very interesting. Yeah, I guess for like, let's say the cybersecurity EVM position, let's say you make more efficient that maybe bunches up like opcodes together, so maybe you execute a bit faster, and that maybe drastically helps simulations because it's a little bit faster. And let's say 10,000 threads running parallel, it might be a marginal benefit to do that. Like, let's say a common opcode pattern, you just convert that into one instead of iterating over 3 opcodes. Now you iterate over one, so you skip a little bit. But I guess let's talk about like the high constraints of like the world. Then it's interesting because you have all the physics and then the chemistry, and I guess all the rules of math as well. It would see why it's so difficult to actually simulate, I guess, the world at mass at very fast paces. Because if we could do that, then would be a lot further than what we are in AI. I assume.
For sure, yeah. Like one of the sort of common sort of epistemic limitations in like, running cheap and easy simulations is something like the 3-body problem from physics. The sort of main takeaway, I mean, like omitting all the mathematical details, the part that's really important is the fact that the consequence of the 3-body problem is that just slight variations in trying to model like, interactions with more than 3 objects basically leads to like complete unpredictability. So like in physics, it's very easy to model interactions between 2 objects. As soon as you add a third, it just becomes completely impossible. And, the real world is very much a multi-object, multi-interaction, high-dimensional sort of like thing. And, this is more or less impossible to model in any reasonable statistical model. And that's actually why AI is so interesting, because you can sort of compress down the real world into such low dimension, at least relative to the dimensionality you need to model the entire world.
Exactly. Yeah, that makes a lot of sense, actually. And that's why we haven't got to like, building humanoid robots that have their own minds and taking over the civilization.
Yeah, it's really hard. It's quite remarkable that, we have a human mind-esque like thing through ChatGPT. I mean, that kind of blew me out of the water.
That's very true. It makes sense. AI applied to like games, I think, completely dominate. So if you have like a specialization, let's say crypto and then AI, and it's a game like environment, which is basically all the blockchains as well, then it's not as insane as, an unbounded is what it seems environment where everything interrelates. But there is like, I guess with blockchains and smart contracts in general, they do all depend on each other in some regard if you want to find an exploit, because they all do interact with each other. And I guess there is multi-dimensions as well. Free.
I'd say the main difference is something like everything within the blockchain space. I mean, okay, first ask the question, what is actually a blockchain? Well, it's a public immutable ledger. That's the important part. And with, censorship resistance and all of these things. And one of the most important parts is that it's public state, right? Everyone can agree on a public state of the blockchain. And so actually the really important part is that, because it's a public blockchain with where you can see the entirety of the state, you can actually include that all within your AI system. And, you have full, complete, perfect information, which is just not the case in the real world, right?
This is true, yeah.
For example, you don't know what's sort of on the other side of your screen because, you don't have the right sensory perception to do it. And even if you try and sort of have a full observation of your entire house, for example, you'll still miss some places. And so this is really what it comes down to with difficulty.
But the dimensions I was talking about though, this is what I was saying with the pillars, is you have, the contracts, each function, and, the call data parameters, and then the state, and the state can change, and that creates an exploit in a certain condition. Those are like 4 dimensions, and they all interact with each other. I know you talked about like, the probability distribution, but that's still a lot of dimensions at the end of the day interacting with each other. So I guess, how do you deal with that then?
Yeah. I mean, like modeling reinforcement learning in high dimensional situations is a problem that has been done multiple times in the past, right? Like, let me give one example, which is something like StarCraft, right? Like StarCraft is this extremely complicated game with like lots of different troops, lots of different positioning, all of these things.
Yep.
And, they like AlphaStar, which is, I think that was DeepMind. That was still able to be done, similar thing, which was done by OpenAI back in the past, like sort of modeling very high dimensional complex things is a thing that has been done. And that's it ultimately always boils down to the fact that software, the cost of simulation is extremely, extremely low. Like it doesn't even cost like a cent, right?
Okay.
It costs fractions of a cent. And so it's really easy to do data acquisition in order to be training models. Whereas the real world just has way too high of a cost prohibitively. That's the main reason.
So if you actually turn the world into a simulation environment somehow, like this is why I was thinking with games, like game environments where they run, I think like Unity, you have like a physics engine and all that that mimics like the real world. Wouldn't that be a step forward in the right direction if you wanted to get to a point where you could sim the world as referencing game engines? Because then it becomes software.
Yeah, so this is what like some people are thinking and trying. I think the verdict is still out on sort of if that is actually achievable or not. I think it'll be I think it'll be hard to say. I mean, if you can do some kind of search on the real space, then that is definitely useful. Like, so to give an example, like the reason why self-driving I'd actually say the cost of simulation is like one of the reasons why self-driving cars really hasn't taken off over the last decade, because the cost of simulation and data acquisition is so prohibitively expensive. And, like often, I mean, in one of Wave, which is like one of the self-driving car startups that I worked at, they built a entire machine learning simulated like simulation environment just so that they can like optimize A, evaluation, and B, training of their self-driving car models in the simulation. And the simulation was like, also a very sort of complicated piece of engineering where it was built using a combination of, Unreal Engine, which is a game engine, combined with sort of like synthetic data generation, both by generative AI, but also just other like AI methods. And so this is how important simulation is. And like the other reason why like simulation is really important and helpful is because like, if you can simulate, you can also plan multiple steps ahead, right? Like one of the remarkable things in AlphaGo was that, that I think not many people appreciate is like just by searching like the AlphaGo AI agent, just by searching 1 minute by running sort of policy-based search, where like they just simulate a bunch of potential futures of like what will happen, they managed to like boost the elo of that AI agent by around 1,000.
Just by simming for 1 minute.
Just by sitting for 1 minute and searching through like multiple different simulations, it increased the elo by 100x bigger.
If you're going through every single path, and then if they do one move and you calculate all the paths relating to that move, what is the higher chance of winning with a rebuttal move? It's very interesting.
Simulation just does improve your like, search capability by a lot. And this is usually what people speculate OpenAI's Q star is about, which is like very much related to
that makes sense.
The reinforcement learning concept of like Q learning combined with A star search, where you basically want to let the AI agent, presumably powered by some kind of LLM, to essentially go search through potential like different fault paths and then try and find the optimal solution as a function of that.
What is your thought? What are your thoughts on like synthetic data for simulation?
Yeah, so I think synthetic data, I think people use the word synthetic data like very willy-nilly. I think synthetic data is sort of like, you can't compare it in an apples to apples comparison. There are some good synthetic data, then there's some bad synthetic data. I'd say like LLM-based output is probably not that high quality in the sense that, you can do garbage in, garbage out.
I think it also is like synthetic data is based on the current model producing that data. If that model is shit, then the data will be shit. It's all like, it can only be as good, if not worse, than the current model creating the data. I think that's the bottleneck.
The sort of devil's advocate case for that particular thing is that, Meta released this sort of AI research recently, which was about, okay, if you get a llama model to spit out some data and another llama model to sort of rate the quality of the data that was output, then you sort of like run the RLHF, training process to improve the language model, then what happens? And it was actually quite remarkable because the results that they managed to get is that the llama model improved in capability up to 3 times, where you just run this process 3 times and it just keeps increasing in capability, measured by, of course, like the standard L benchmarks, which are slightly dubious, but certainly are decent benchmarking methods. So, I think that the jury's still out on sort of LLM created synthetic data. This will be something we won't know for a while.
Okay, got you. And I think some final questions. Since you guys are hiring at GatlingX and people might be interested to get in and join your team, what are the key skills you're looking for? I know you're doing the DevOps and the RL engineer and a few others, but let's say someone wanted to get to like your level of understanding and what you're doing in, let's say, AI, GPUs, cybersecurity. What do you kind of recommend for people to get to this level if they're not already there or very close to it?
Yeah, I mean, I think like specializing very deeply into something probably helps. I mean, like I specialize very heavily in like AI and robotics and just sort of followed where my curiosity went. And I think doing really hard things, being surrounded by really competent people is like a really effective way to learn. I think, I am probably the least capable person in GatlingX, and that's sort of the bar that we want to try and maintain. And I think doing really hard things with really sort of smart people, I think, is the best way around these kind of like, how can you learn? What's the best thing to do? Yeah, it's just to dive deep and try and understand it as well as you can and talk to the people who are the best at it. I think those are usually the methods we go for. But yeah, I mean, if anyone's good at sort of symbolic solving or DevOps or RL or just generalist C++ stuff, we are hiring as well.
Perfect. And just to follow up with that one as well, when you are trying to create a thorough understanding of something, what do you think are like the main characteristics you need and things to do on, like, let's say, a daily basis to really get there? My thing is always consistency, no matter how small, just do it every day. But maybe you have some other methods as well to optimize for learning and understanding.
I think, I always find that talking and being surrounded by smart people is usually the best method. I think that, like, when you're in an environment where, like, everyone else around you can learn from, and they are smarter than you in different things, then there's a tremendous benefit that you just get. Because, we're all human. You sort of always need human interaction. And if you can also learn from your human interactions that are sort of necessary for you, then I think that has a compounding effect. So I would actually follow on your answer and say it's actually creating the optimal environment where you don't even need to be consistent. You will just be consistent by design. By environmental design, I think is the best way forward.
And I think that also goes into online as well. It's just joining communities and surrounding yourself with these like-minded people or people you want to become or be similar to. I think that's also a big factor, which I didn't really know the value of when I first started getting into crypto. It's as if you surround yourself with a bunch of millionaires, you're bound to become a millionaire, right? Same with drug addicts. So it definitely is a big psychological thing, and you are who you're mostly around, right? So
yeah, I think we're like human beings are highly mimetic creatures, and coming to accept that, I think, is a really good sort of starting point.
For sure, man. Eito, thank you so much for jumping on. I really appreciate it. I've learned a lot, and I'm sure a lot of people that are listening are very fascinated with what you're doing and the background of yourself and GatlingX. If anyone is keen of joining, go look at the jobs board. Hopefully you can get in and do some cool stuff with the GPU fuzzing things. Man, again, thank you so much for jumping on.
Many more than that, man. There's so much you can do with the GPU-EVM. Like, We only scratched the tip of the iceberg.
Only the tip, just the tip. We need to get your fellow workers on to do a follow-up then.
Yeah,
We'll see.
hopefully.
I'm sure we'll have another one down the road as well, because you only just launched, so I'm sure down the road we'll have another one as well.
Yeah, awesome.
Thank you so much, and take care, everyone. GNGN.